Hi everyone, this will be your video for the Squeeze Theorem. You'll see one example in here, and you can also look on the book's website, larsoncalculus.com, for more proofs and examples. So here we have the theorem written out. I know this is usually a little bit different than what we see, but I think this really exemplifies this theorem perfectly. So you're going to have three functions. You're going to have h of x and g of x, and f of x is in the middle, and you can see this because we have our less than or equal to sign, less than or equal to sign, they go consecutively. If we were to look at a graph of these, the way that we have this written out, g of x is the greatest, so that'll be most towards the top of your coordinate plane. H of x is the least, so that'll be more towards the bottom, and f of x is just in the middle there somewhere. So our g of x I'm going to write in red. That could be anything, right? It could go like this and go onwards. And then we also have our h of x, which I'm going to highlight in blue, and that's going to be below because we said it's going to be less than. And then finally we have our f of x, which is right in the middle, and that f of x, you can do anything at once in here, but it's going to get squeezed between g and h. There will be one point that if the squeeze theorem applies, where their limits will all be equal, and that's what's written in this next line here, is that if they are set up like this, where you have your greatest function, your least function, and you have one more function in the middle, if you're finding the limit at a certain value of c for h, and your limit at a certain value of c for g, and their limits are the same, pretty much like what I pictured over here, this limit for g is going to be the same as your limit for h. That also means that our limit for f is squeezed in the middle there. So that's why this is called the squeeze theorem, because they can almost pinch together at one point and share the same limit. So that's telling us that if h and g have the same limit L, we could also say that that is the limit of f of x. So here we have an example of a problem that you would see most often in your work. And this problem is asking us, I didn't have a chance to fit it on here, but it's asking us for the limit as x approaches c of f of x. Now the reason that we do need the squeeze theorem is because we don't have a function for f of x, we just know that it's between these other two functions. So here's what you need to do. So step one, we're going to find limit of h of x. So h of x is the one that's least. Remember we highlighted that in blue, so that's going to be this one down here. So we're going to find the limit as x approaches 0 of 4 minus x squared. So using our new notation where we know that we can just plug in 0 analytically, and if it works, then it works. When I plug in 0, I have 4 minus 0 squared, and I get 4. Our second step is going to be to find the limit of g of x. G of x was our greatest function, so g greatest, which we highlighted in red. So we'll do this one. We're going to find the limit as x approaches 0 of our g of x function, which was 4 plus x squared. So again, we can do this analytically, you could do this graphically, but now that we know analytically, we always try that first. Try that direct substitution. This works out for us. We get another 4. So this is like a humongous relief, right? When you see that these two values are equal, that means that we can for a fact say that we know that this is what the limit of f of x is. Okay, so if results from steps 1 and 2 are equal, that is your solution. So for us, we were looking for the limit as x approaches 0 of our f of x, and we don't even know that function, so we can't plug in 0. But by using the squeeze theorem, we know that if the limit from a function less than f of x is 4, and the limit of a function greater than x is 4, then it's going to be 4.